Learning Semantic-Agnostic and Spatial-Aware Representation for Generalizable Visual Audio Navigation. Submission to IEEE Robotics and Automation Letters 2023. Visual audio navigation is attracting more and more attention from the robotic community, due to its broad applications such as household robots and rescue robots. In this task, the agent should navigate to the sound source with visual and audio observations.
In the right figure, the agent is in the bedroom initially, and the sound source is in its front left direction.
Here we present a demo of an agent navigating to a horn sound. Key problems in visual audio navigation are generalizing the policy to sounds that have never been heard before and low sample efficiency. Existing methods do not have specific designs to tackle these problems. Inspired by the dual pathway model of the auditory process in the human brain, we divide the content in sounds into semantic and spatial components and treat these two components differently. The red part in the figure is the dorsal streams that process semantic information, and the green part in the figure is the ventral streams that process spatial information. Since the semantic information changes as the sound category changes, the spatial information remains the same. Thus, if the agent can be aware of the spatial information and be agnostic to the semantic information, the learned policy can be generalizable to unheard sounds. To tackle the generalization problem and improve sample efficiency, we designed two auxiliary tasks. The green branch in the figure is semantic-agnostic learning. In this task, we design an audio classifier to distinguish the audio features generated by an audio encoder. We add a gradient reversal layer between the audio encoder and the audio classifier to maintain an adversarial relationship. If the accuracy of the audio classifier is low, we argue that the audio encoder is semantic-agnostic. The red branch is spatial-aware learning. We design the location predictor to estimate the sound source direction. This module can provide an extra training signal for extracting spatial information to assist navigation policy learning. The inherent logic of this method is implicit in the way humans process sound. And the experimental results also demonstrate its effectiveness. Since our method is plug and play, we apply our method on AVNav and AVWAN and evaluate them in unheard sounds. The results show our method improves the performance in Replica and Matterport 3D. Our method learns a generalizable and efficient policy. We perform ablation studies on audio classifiers and the location predictor components of our method. The results show that removing either the audio classifier or the location predictor reduces performance. To demonstrate that our method has better sample efficiency, we show the learning curve on the testing set on the Replica and Matterport 3D with both AVNav and AVWAN as backbones. The result shows that our method can achieve higher performance than the final results of the original method, with fewer samples than the original method needs to get converged. The following slides show the particular trajectories. We will compare the consistency and efficiency of the trajectories of our method and AVNav for different sounds. After the same training steps, the navigation trajectory obtained by our method is more closely matched to the shortest path, showing high sample efficiency. In contrast, the original method may take a complex route or even fail in some tasks such as the first 3 columns. What's more, the trajectories generated by our method under different sound categories show high consistency. These consistency trajectories suggest that the representations used for decision-making are similar and experimentally demonstrate that the learned representations are semantic-agnostic. Thank you for watching.